Well, okay. Sorry about that. If you watched the last video, some stupid flashlight thing turned on, and it came back. So here we go. Let's talk about increasing and decreasing functions. Welcome back. This is chapter 5.2 of our calculus book. You can read the description of the video if you want to know what book we're using. And we're going to do something here that's one of these sort of like weird mathy things where we say something completely obvious and then we prove it. So here's the completely obvious statement. F is a function on some interval, I, and 1 if x1 is less than x2, in other words, moving to the right, and f of x1 is less than f of x2, f is an increasing function. No kidding. But hey, I told you we were going to prove something that seems self-evident. 2, if f1 is less than x2 and f of x1 is greater than f of x2, f is a decreasing function. Here's the thing about math. First off, I'm not a mathematician, I'm an engineer. We don't worry quite as much about this stuff. But mathematicians, you can't just say this is true. You prove it's true, and then from then on, you can assume it. And so that's where this comes into play. So what this then leads to, and we'll have a proof in just a second, what this then leads to is that if f of x1 is less than f of x2, this means that f prime of x must be positive. And if f of x1 is greater than f of x2, f prime of x is negative. And this just comes from the definition of derivative. And if you think about the definition of derivative, f of x plus h minus f of x divided by h, the limit as h goes to 0. Well, if we consider this to be x2 and this to be x1, if x2 is f of x2 is greater, function's going up. F of x2 lesser, function going down, and more importantly, positive derivative and negative derivative. So let's prove this using the mean value theorem just for fun, because, you know, it's sort of nice to be exposed to some of these proofs every once in a while. Let's let x1 and x2 be 2 points in the interval AB. And x1 is less than x2. So we're moving from left to right on our graph. F prime of C is equal to f of x2 minus f of x1 divided by x2 minus x1. All right. We are going to also assume that f is continuous and differentiable because we want the mean value theorem to apply. So let's do a little algebra here. F prime of C times x2 minus x1 is equal to f of x2 minus f of x1. Well, this is always positive. which means that the derivative has the same sign as the difference. Same sign. For an increasing function, f of x2 is greater than f of x1, which implies positive. And for decreasing, f of x2 is less than f of x1, which implies the derivative is negative. There you go. Beautiful proof. Simple, straightforward, didn't take much. Let's look at an example of why we care. So example 5, here we've got y equals x squared. Where is it increasing and where is it decreasing? We already know the answer to this. Increasing to the right of 0, decreasing to the left of 0. But let's look at the derivative. Y prime equals 2x. 2x is less than 0 when x less than 0. 2x is greater than 0 when x is greater than 0. So not super interesting, but we know that on this interval, this is a decreasing function. And we know that on this interval, this is an increasing function. Now, here's where it becomes more interesting. Let's look at a more complicated function. Oh, well, know what? We'll come back with a more complicated function. Why don't you guys do exercise 15 in the book? And the function that we will come back with as example 6 is f of x equals x cubed minus 4x. So very quickly, the derivative of this function is 3x squared minus 4. I want to know where this is greater than 0, and I want to know where this is less than 0. One strategy, and the strategy I like, is to start by finding out where it is equal to 0. And we get is that x squared is equal to 4/3, which means that x equals plus or minus the square root of 4/3. Equal to 0. Square root 4/3 negative and square root 4/3 positive. And now I can do a little analysis. And of course, if x squared is equal to 4/3 here, then x squared must be greater than 4/3 over here. So this is greater than 0 and greater than 0. You know what? I'm going to change colors to do that so that it's a little more obvious. This function must be greater than 0 here and greater than 0 here, and the function must be less than 0 here. So why is this interesting? Well, let's think about a graph of this function. This function is increasing right up to negative square root 4/3, and it is decreasing right down to positive 4/3, and then it increases again. And since I know a cubic's end behavior is down to the left, up to the right, I know that this is negative root 4/3, and that this x value must be positive root 4/3. And even though I don't know the height of the graph, I now know the shape of the graph, and I know where it turns over. All right. Go ahead and do exercise 27. And oh, by the way, if you were asked about increasing and decreasing, now would be the appropriate time to do intervals. There's decreasing, there's increasing, here's decreasing, and then here's another increasing interval. So remember to answer the question which is asked. Question asked being, where is it increasing, where is it decreasing? And I'm going to go ahead and stop this video. We'll be back with a little bit more about things that you can determine based off of the mean value theorem.